Forget every number you think you know. Forget every distance you've ever pictured, every road trip, every flight across an ocean, every mental image of space you built from a textbook diagram or a science fiction movie. None of it prepares you for what's coming. Every reference point you own is a rounding error, a speck of dust resting on something so enormous that the word enormous stops carrying any weight. What you're about to hear is not exaggeration. It is measurement. Careful, tested, repeatedly confirmed measurement. Spans roughly 93 billion light-years from one side to the other. That is the calculated width of everything light has had time to bring us since the beginning of time itself. And here's the detail that should unsettle you a little. Most researchers now believe the true universe, the part that lies beyond the reach of any telescope we will ever build, is at least 250 times larger than that. Some models don't stop at large. They stop at endless. This is a trip through every layer of scale that exists, starting somewhere your instincts still function. We begin on solid ground, on a planet you already understand, and we work outward past the edge of our solar system, past a galaxy holding hundreds of billions of suns, past a cluster of galaxies bound to us by gravity, past a supercluster spanning hundreds of millions of light-years, out to the largest structure ever mapped, a web of matter stretching across the observable sky. And then, because the observable sky is itself a tiny fraction of what's actually out there, we keep going past that too. Settle in. You live on a spinning ball of rock and metal, coated in a thin skin of water and air, rotating at something like 1,600 kilometers an hour if you happen to be standing near the equator. You've never felt it. Nobody has. The ground reads as still. The horizon reads as flat. For nearly the entirety of human history, that illusion was the whole of reality, and it was enough. Entire civilizations rose and fell without anyone needing to reckon with the fact that their world was a sphere hurtling through the dark. Our planet measures about 12,700 kilometers across at its widest point, and its circumference, the distance if you walked its fattest belt all the way around, comes out to roughly 40,000 kilometers. Start walking today, never resting, never eating, moving across open water as if it weren't there, and you'd need about a year of non-stop motion to arrive back at your starting line. Earth is large by any standard a walking creature can appreciate. It's large enough that most people, for most of history, never traveled more than a day's journey from their birthplace. It happens to be the biggest and densest of the rocky worlds in our solar neighborhood, which sounds like an achievement until you realize the competition barely qualifies as competition. Start with the world closest to the sun. It's a scorched, airless ball a little over a third the width of Earth, tidally bound so tightly to its star that one side bakes while the other freezes in permanent shadow. Stand on its surface, if you could survive there for even a heartbeat, and the sun would appear more than double the size it does from home, a furnace filling the sky. Move outward, and you find a planet almost exactly Earth's twin in size, and almost nothing like it in any other respect. Its atmosphere is a crushing shroud of carbon dioxide thick enough to flatten a submarine, its clouds laced with sulfuric acid, its surface hot enough to melt lead. Early landers sent by human engineers lasted less than 2 hours before the heat cooked their circuits. This world spins backward, and so slowly that a single day there lasts longer than its entire year. It is what happens when a planet everything possibly goes wrong. Farther out sits the rust-colored world, roughly half of Earth's diameter, its red hue coming from iron oxide coating its dust the way rust coats an old car left out in the weather. It carries the largest volcano known in our solar system, a mountain so vast it could blanket an entire American state and stand nearly 3 times the height of the tallest peak on Earth. It has canyon systems that make our own grandest gorge look like a scratch in the dirt, and it's brutally cold, with an atmosphere so thin that unprotected human blood would boil there, not from heat, but from the near-total absence of pressure holding it in liquid form. Then come the giants. One of them stretches across nearly 143,000 kilometers, 11 Earths lined up edge to edge just to match its width, and more than 1,400 Earths could be packed inside its volume. It has no solid ground to stand on at all, just endless layers of hydrogen and helium, storms with winds faster than sound, and pressure that eventually turns gas into something behaving like liquid metal deep in its interior. It radiates more heat than it receives from the sun, a leftover glow from its own formation, a world that almost became a star and never quite got there. Its ringed neighbor is nearly as wide, spanning some 120,000 kilometers. yet in most places no thicker than a skyscraper is tall. This world is so light for its size that if you found an ocean vast enough, it would float. Beyond that sits a pale blue-green sphere tipped completely onto its side, its poles taking turns facing the sun directly, for reasons nobody has fully explained. The leading guess is an ancient, violent collision that knocked it over, and it never recovered. And past that, a slightly smaller but denser world of icy blue that marks the outer edge of the planetary system, so far from the sun that sunlight takes over 4 hours to reach it. From out there, you can barely picture them without a shortcut. Astronomers measure the space between our planet and the sun, roughly 150 million kilometers, and call that single unit an astronomical unit, using it as a ruler for everything else nearby. On that scale, the innermost world sits at roughly 4/10 of a unit from the sun, the outer ice giant at about 30. Even under ideal alignment, reaching the red planet from here means crossing more than 50 million kilometers, and if you miss that window, the trip stretches past 400 million. One of the fastest machines humanity has ever launched needed roughly a decade just to reach the dwarf world orbiting far beyond the ice giants. And that dwarf world isn't remotely close to the true edge of our solar system. The actual boundary, the place where the sun's gravity finally loosens its grip and interstellar space takes over, is a vast shell of icy debris left over from the system's formation. It begins roughly 2,000 times farther from the sun than Earth is, and stretches outward to somewhere around 100,000 times that distance, which translates to something like 1.5 to 3 light years. A light year, for reference, is the distance light itself covers in a single year, while moving at 300,000 kilometers every second, about 9.5 trillion kilometers. The fastest spacecraft ever launched, moving at roughly 58,000 kilometers an hour, would need about 30,000 years just to reach the inner edge of that icy shell. By the time it arrived, every human alive today would have been gone for 28,000 years. Most of the solar system, in other words, is empty. Profoundly, almost unsettlingly empty. A dozen people have walked on its surface. The last one left in the early 1970s, and in the decades since we've stayed close to home, circling our own planet like a dog that never leaves the yard. And towering above all of it sits the sun itself, spanning nearly 1.5 million kilometers, about 109 times the width of Earth. You could fit roughly 1 million Earths inside it, or about 1,000 of the largest gas giant in our system. It holds almost all, nearly 99.9%, of the total mass in our solar system. It's a star, with some debris caught in its gravity. From Earth, that star dominates everything. It's the reason anything here is alive at all. But step back far enough, and its dominance fades. Seen from the outer ice giant, it shrinks to a fraction of its usual brightness. Step back farther still, out toward that icy shell at the true edge of the system, and it becomes just another point of light among the stars, indistinguishable to the untrained eye. The thing that makes our entire existence possible is, from a modest distance, unremarkable. There are stars out there hundreds of times its size, thousands of times more luminous, stars so enormous that if you swapped one in for our own, its outer surface would extend past the orbit of the red planet. And those stars are common. We simply can't see most of them because the distances involved put them far beyond naked eye visibility. We haven't even left our own driveway yet, and already the scale has broken most people's sense of what big means. That icy shell at the edge of our system stretches across multiple light years, meaning light, the fastest thing that exists, needs years just to cross the width of our own solar system's gravitational reach. And that entire zone, mostly emptiness with a scattering of frozen debris at its rim, belongs to a single ordinary star. There are more stars in the portion of the universe we can observe than there are grains of sand on every beach and every desert on this planet combined. Each one of those stars, in principle, has its own version of everything we just described. Its own planets, its own icy debris field, its own edge where starlight fades into darkness. Our solar system isn't small. By any measure a human mind evolved to handle, it's staggering. And it is also nothing at all, a single day. Leave the sun behind and look at the neighborhood of stars around it, the beginning of a much bigger structure, the one we call home. Our galaxy is often described the way an island is described, something surrounded by an ocean of darkness so vast that other islands might as well not exist. That phrase fell out of favor once astronomers realized the ocean is packed with other islands, billions of them, spaced apart by distances so extreme that their light takes eons to cross the gap. But the old comparison still captures something true, because from inside our galaxy, we can't step back and see its outline the way you'd see a photograph. We're standing on its shoreline, describing the shape of the whole coastline from memory, piecing it together star by star, using careful measurement to build a map of something too enormous to view directly. Our galaxy is a barred spiral, meaning it has long, sweeping arms of stars and gas curling outward from its center like water circling a drain, and at its heart, a thick, dense bar of older stars packed together in a rough rectangular shape. That bar channels gas inward, feeding new star formation near the core, and pushes matter outward along the arms, seeding star birth in the denser lanes. The whole structure turns slowly, not as a solid disk, but as billions of individual stars, each tracing its own orbit, moving at slightly different speeds depending on how far out it sits. It looks frozen in photographs. It isn't. It's in constant, gradual motion, a pattern of light reshaping itself over millions of years. Our galaxy spans somewhere around 100,000 light-years across, and some newer measurements push that figure higher still. 100,000 light-years. Try holding that shape in your mind, and notice your brain quietly giving up and filing it under very large, before moving on. That's normal. Our minds evolved to judge the distance to the next hill, the next river, the rustle in the grass that might be a threat. They were never built to hold a number like that. And yet this galaxy is not abstract. It's real, wrapped around you right now, invisible in daylight but there all the same. Every star you've ever picked out in a night sky, every shape people have traced into constellations across every culture and history, belongs to this one structure. Most nights, most people never even glimpse it, because from a genuinely dark sky far from artificial light, you can make out a faint pale band stretching overhead. Ancient cultures gave it names describing rivers, roads, and rivers of milk, each one describing the same phenomenon, the combined, blurred glow of billions of stars too distant and too faint to pick out individually. That band is the edge-on view of our galaxy's flat disk, seen from inside it, looking along its length. It's thin, something like 1,000 light-years thick, wide in two directions and narrow in the third, like a dinner plate. But most people alive today have never actually seen it. City lighting washes the sky into a flat orange haze, drowning out everything but the brightest stars and planets. Whole generations have grown up assuming the night sky is supposed to look nearly empty, that a photograph of a truly dark sky, packed with stars, must be doctored or exaggerated. It isn't. We've simply covered up our own view of the universe with the glow of our own cities. On the clearest, darkest night, unaided human eyes can pick out perhaps 2,000 or 3,000 stars. Our galaxy holds somewhere between 100 and 400 billion of them, with most estimates landing near 200 billion. Do the arithmetic, and what you can actually see amounts to a small fraction of a single %. You are looking at almost nothing, a handful of the closest, brightest neighbors, while an entire galaxy of light sits invisible behind them. It's not just stars either. For roughly every star, there's likely at least one planet, and probably more. Conservative counts put the number of planets in our galaxy around 100 billion. More generous ones push past 400 billion. A space telescope that spent 4 years staring at a single patch of sky containing about 150,000 stars turned up more than 2,600 confirmed planets in that one narrow slice alone. Multiply that across the whole galaxy, and the totals become almost meaningless. Hundreds of billions of worlds, most of which will never receive a name, never be visited, never be seen by anything capable of wondering about them. Our solar system sits roughly 27,000 light-years from the galactic center, not in the crowded downtown, not at the sparse outer edge, but somewhere in the middle suburbs, tucked into a minor spur of a spiral arm connecting two larger structures. That local spur stretches a few thousand light-years across and roughly 10,000 long, home to a few 100 million stars, including nearly every bright star you've ever named by looking up. The nearest bright star sits a little over 8 light-years away. A famous red giant in a well-known constellation sits around 550 light-years out. Even these close neighbors are so distant that a spacecraft moving faster than anything else humanity has built would still need on the order of 70,000 years to reach the very nearest one. Our star carries the entire solar system around the galactic center at roughly 800,000 kilometers an hour, and you never feel a thing, because everything around. One full circuit of the galaxy takes about 250 million years, a span astronomers sometimes call a galactic year. The last time our sun sat in this exact position relative to the galactic core, dinosaurs were just beginning to diversify, and the continents were still mostly fused together. Since our planet formed some 4.5 billion years ago, it has completed a little more than 18 of these galactic years. Modern humans, by comparison, have existed for perhaps 300,000 years, a sliver representing roughly 0.1% of a single galactic orbit. At the very center of our galaxy sits something we can't observe directly with visible light, because thick clouds of dust block the view. But other wavelengths, radio, infrared, X-ray, reveal a supermassive black hole weighing somewhere around 4 million times the mass of our sun. Its event horizon, the boundary past which nothing, not even light, can escape, spans roughly 23 million kilometers. Drop that object into the middle of our solar system, and its boundary would stretch almost to the innermost planet's orbit. Astronomers first detected this object as a mysterious radio source decades ago, but it took careful tracking of stars whipping around it at incredible speeds, one completing a full orbit in as little as 16 years, to confirm what had to be sitting there, an object so massive and so compact that nothing else could explain the motion. That discovery eventually earned a share of a Nobel Prize. Most of our galaxy's mass isn't found in stars, gas, dust, or even that central black hole. It's something we still can't see directly. Stars near the outer edges of galaxies move far too quickly to stay bound by the gravity of the visible matter alone. Something unseen has to be holding them in place. Estimates suggest this invisible material makes up somewhere between 85 and 90% of our galaxy's total mass, spread through a vast halo extending well beyond the visible disk. Every measurement of the galaxy's total weight is, in a sense, an educated guess, sophisticated, carefully calculated, backed by decades of data, but a guess nonetheless because we're trying to weigh a structure from deep inside it. One influential estimate placed our galaxy's total mass, including all of that invisible material, at roughly 130 trillion times the sun's mass. A more recent study using better measurements of outer stellar motion revised that figure sharply downward to something closer to 1/10 of the original number. Even the smaller figure remains almost impossible to picture. Our galaxy isn't a finished object either. It grows by consuming smaller neighbors, tearing them apart with gravity and scattering their stars into its own structure. We can watch this happening right now. A small companion galaxy passing repeatedly through our galactic disk is slowly being shredded, its stars stretched into long streams wrapping around us like ribbons, destined to become indistinguishable from our own galaxy's outer halo. And in roughly 4.5 billion years, our entire galaxy is on a collision course with the next large spiral over, sitting some 2.5 million light-years away. Collision is misleading. Galaxies don't crash the way solid objects do. Stars are spaced so far apart that almost none of them will actually strike each other. Instead, gravity will scramble both galaxies together over hundreds of millions of years, triggering bursts of new star formation where gas clouds collide, flinging stars into unfamiliar orbits, and eventually merging the two spirals into one enormous, structureless elliptical galaxy. Our own sun, if it still exists by then, will likely already be nearing the end of its life, swelling into a red giant, and our planet, if anything of it remains, will be a scorched, lifeless cinder. Our galaxy still forms new stars, roughly 7 per year, a trickle against a backdrop of 200 billion existing ones, essentially balanced by the rate at which older stars die. Eventually, over trillions of years, that balance will tip. The gas needed to build new stars will run out. Star formation will slow and then stop, and the galaxy will fade into a slow, dark graveyard of dead stellar remnants. That ending lies unimaginably far in the future, long after every structure humans have ever built has crumbled to dust. But it's coming, on a timescale that makes human history look instantaneous. For all its grandeur, our galaxy is not alone. It belongs to a loose, gravitationally bound cluster of galaxies, a modest cosmic neighborhood spanning roughly 10 million light-years across. Early catalogs of this cluster listed a dozen members. Better instruments eventually pushed that number into the dozens, and current counts sit somewhere between 50 and well over 100, depending on how faint an object has to be before it counts as a genuine galaxy, rather than a stray stream of stars. Most of these are small, dim dwarf galaxies holding only a few million to a few billion stars each. Two massive spirals dominate this neighborhood. our own, and a larger one visible even to the naked eye on a clear night as a faint smudge of light, the most distant object most people will ever see without a telescope. The light reaching your eye from that smudge left its source roughly 2.5 million years ago, long before anything resembling a modern human existed. That neighboring galaxy is wider than ours, holds perhaps 1 trillion stars to our 200 billion, and is approaching us at more than 100 kilometers every second, closing a gap that has been narrowing for billions of years, and will finally reach zero in roughly 4 billion more, resulting in the merger already described. A third, smaller spiral orbits that larger galaxy and may get pulled into the eventual merger, or flung out into the darkness between galaxies entirely. Simulations can't yet say which. Closer to home, 2 irregular companion galaxies orbit our own like oversized moons, visible from the southern hemisphere as detached patches of light near the main band of our galaxy. They hold tens of billions of stars between them and are slowly being torn apart by our galaxy's gravity, their material already stretching into thin trailing streams that will eventually be absorbed entirely. The smallest known member of our local neighborhood contains only about 1,000 stars. Fewer people than live in a small town, few enough that you could, in principle, count them one at a time. Whether something that small should even be called a galaxy rather than a dense star cluster remains genuinely debated among astronomers. Even with dozens of member galaxies, most of the volume inside this 10 million light-year neighborhood is empty. Add up every star in every galaxy within it, and you land somewhere around 1 to 1.5 trillion stars. An enormous number that becomes almost nothing once spread across that much space. You could travel through this neighborhood in a straight line for millions of years at the speed of light, and most of the time encounter absolutely nothing. But even this neighborhood is not the top of the hierarchy. It's held together by gravity, and it's being pulled, along with thousands of other similar neighborhoods, toward a much larger structure. That structure wasn't even properly identified and named until 2014, when a team led by an astronomer working in Hawaii mapped not just the positions of nearby galaxies, but their motion. Using a technique borrowed from the study of water drainage patterns on land, the team traced the boundaries where one gravitational basin ends and another begins, and identified the true supercluster containing our galactic neighborhood. They gave it a Hawaiian name meaning something like immense heaven, honoring both the team's home institution and the long tradition of Hawaiian navigators who once crossed vast stretches of open ocean by reading the sky. That supercluster spans something on the order of 500 million light-years and contains roughly 100,000 galaxies, adding up to something in the neighborhood of 1,250,000,000 stars or more. Compared to that scale, the gap between our galaxy and its nearest large neighbor, that 2.5 million light-year distance that seemed so vast a moment ago, becomes a single pixel in a much larger picture. The total mass of this supercluster, including every star, every wisp of gas, and all of its invisible dark matter, comes out to something like 100 quadrillion times the mass of our Sun, roughly 100,000 times heavier than our entire galaxy on its own. Near the center of this structure sits a genuine gravitational anomaly, an enormous concentration of mass, hidden partly behind the obscuring dust of our own galaxy's disk, pulling our entire local neighborhood toward it at something like 600 kilometers per second. We've been falling toward it for billions of years, and will keep falling for billions more, not because of any choice, but simply because that's what gravity does. It took decades of work with instruments capable of seeing through interstellar dust to finally locate the massive cluster of galaxies responsible for much of that pull, sitting a couple 100 million light-years away in that general direction. And even that turned out to be only part of the story, one piece of a broader concentration of galaxy clusters, all pulling together toward the same gravitational center, which itself is being tugged towards something even larger and farther away. Here's the uncomfortable twist. Unlike our tightly bound local galactic neighborhood, this larger supercluster isn't actually held together for the long haul. The expansion of space itself is stronger than the gravity binding it, and that expansion is speeding up, driven by a mysterious force researchers call dark energy, a force that now accounts for roughly 2/3 of all the energy in the universe, dwarfing both ordinary matter and the unseen dark matter combined. Because of this, the supercluster we call home is slowly coming apart at the seams, not through any violent event, but through simple, patient stretching. Over tens of billions of years, its outlying galaxies will be carried beyond the range where their light can ever reach us again, and the structure as a coherent thing will effectively cease to exist. not destroyed, just gradually dissolved by the growth of space itself. Zoom out even farther, and a genuinely different kind of pattern comes into focus. Not a hierarchy of separate nested objects, but a continuous, interconnected web spanning the entire observable sky. Long, thin filaments of galaxies and invisible matter stretch across hundreds of millions of light years, connecting dense clusters like threads between cities. Between those filaments lie enormous voids, regions of space so empty that they contain only a tiny fraction of the galaxies you'd expect to find there, based on the universe's average density. And where multiple filaments cross, matter piles up into massive galaxy clusters, some weighing more than 1,000 trillion suns. This pattern wasn't obvious until astronomers began systematically mapping the distances to enormous numbers of galaxies, starting in earnest in the 1980s and expanding dramatically, with a major sky survey launched at the start of this century that eventually charted the positions of millions of galaxies across a huge volume of space. What emerged looked less like a random scattering of light and more like a sponge, or a spiderweb, threads of galaxies wrapped around gigantic bubbles of near-nothingness. Computer simulations starting from tiny density variations left over from the very beginning of the universe, and run forward under the influence of gravity alone. It's the inevitable outcome of gravity acting on matter that wasn't perfectly evenly distributed to begin with. Roughly 70% of the total volume of the universe consists of these voids, near total vacuum, sparsely populated by isolated, starved dwarf galaxies with no neighbors for tens of millions of light years in any direction. Most of the remaining volume is threaded by filaments, which alone contain roughly half of all the ordinary matter in the universe, despite occupying a small fraction of its space. And the dense knots where filaments intersect, occupying less than 1% of the total volume, hold roughly a tenth of all the matter there is. This entire structure is scaffolded by dark matter, which collapses more easily than ordinary matter because it isn't slowed by pressure or heat the way gas is. Ordinary matter, the stuff that becomes stars and planets and eventually people, simply falls into the gravitational wells that dark matter carves out first, lighting up wherever the invisible material is thickest. This web is not static. It's a slow-motion flow system, funneling gas and galaxies from the empty voids toward the dense filaments and finally into the crowded nodes, over timescales of billions of years. And it is, by a wide margin, the largest coherent structure we know of. Not an object with a boundary, but the underlying architecture on which every galaxy, every cluster, and every supercluster we've discussed is strung like beads. Even this cosmic web, though, sits inside something with an actual edge. Not an edge in the sense of a wall, but a horizon, defined not by structure but by time and light. The portion of the universe we can even in principle ever observe has a radius of about 46.5 billion light-years, giving it a total diameter of roughly 93 billion light-years. That number seems impossible at first glance, because the universe itself is only 8 billion years old, meaning light has only had 13.8 billion years to travel. So how can the visible edge sit more than 3 times farther away than that? The answer lies in the fact that space itself has been stretching the entire time that light has been in transit. Picture 2 dots drawn on the surface of a balloon. Inflate the balloon, and the dots drift apart, not because either one is moving across the rubber, but because the rubber itself is expanding beneath them. Distant galaxies work the same way. A galaxy whose light left it billions of years ago, when the universe was much smaller and more compact, has since been carried much farther away by the ongoing expansion of space, meaning the actual current distance to that galaxy is far greater than the distance its light traveled to reach us. That gap between how far the light traveled and how far the source actually is now accounts for the difference between 13.8 billion years of travel time and 46.5 billion light-years of present-day distance. This expansion isn't slowing down either, it's accelerating, driven by that same mysterious dark energy, which now makes up roughly 2/3 of the total energy content of the universe, with the unseen dark matter making up most of the rest, and ordinary visible matter accounting for less than 5% of everything that exists. The rate of this expansion, once you get far enough out, actually exceeds the speed of light, not because anything is physically moving faster than light through space, but because space itself is growing between us and those distant points faster than light can cross the widening gap. Past a certain distance, roughly 16 billion light-years out, any light being emitted right now will never reach us at all. those regions have effectively crossed a cosmic point of no return, visible to us only as they were in the deep past, frozen in the light that managed to escape before the gap grew too wide. Every time you look at a distant object, you're looking backward in time. Look at our own sun and you see it as it was 8 minutes ago. Look at the nearest star beyond our system, and you see it as it was 2.5 million years in the past. Look at the very edge of what we can observe, the faint, ancient afterglow left over from roughly 380,000 years after the universe began, back before atoms had even fully formed and space was still an opaque, glowing fog. And you're looking at light that has been traveling for essentially the entire age of the universe, stretched by expansion from its original wavelength into the microwave portion of the spectrum by the time it finally reaches a telescope. That faint microwave glow is our absolute horizon, not because nothing exists beyond it, but because before that, the total amount of ordinary matter packed into the observable universe is almost impossible to write out in a way that means anything. Something on the order of 1.5 times 10 to the 53rd power kilograms, spread across roughly 2 trillion galaxies, adding up to something like 10 to the 24th stars, a trillion of them, give or take. And this entire staggering total, this sphere 93 billion light-years across, packed with 2 trillion galaxies, is shrinking in terms of what remains visible to us, even as the true universe keeps growing. Eventually, tens of billions of years from now, almost nothing beyond our own immediate galactic neighborhood will remain visible from Earth. Any civilization looking up at that point will see a nearly empty sky and have no way of knowing that a vast, structured universe ever existed beyond it. We happen to be living during one of the eras when that evidence is still visible. A temporary window, closing a little more every year. A powerful modern space telescope, launched at the end of 2021 and now stationed roughly 1.5 million kilometers from Earth, was built specifically to peer deeper into that ancient light than any instrument before it. Rather than observing mostly visible light the way earlier space telescopes did, it's tuned to infrared wavelengths. Because the light from the most distant galaxies has been stretched so dramatically by cosmic expansion that it arrives not as visible light at all, but as infrared, invisible to the human eye and to older instruments. Shielded from the sun by a 5-layer sun shield roughly the size of a tennis court and cooled to hundreds of degrees below zero, this telescope's mirror, spanning about 6.5 meters, assembled from 18 gold-coated hexagonal segments that had to unfold perfectly in space after launch, gathers roughly 6 times more light than its predecessor, letting it detect objects around 100 times fainter. And what it's found has upended some long-standing assumptions. It has spotted galaxies existing less than 300 million years after the universe began, a sliver of cosmic time in which, according to older models, only small, disorganized clumps of early stars should have had time to form. Instead, some of these earliest galaxies appear surprisingly large, surprisingly bright, and in some cases already containing heavier elements that can only be forged inside stars and then scattered by stellar explosions. Meaning entire generations of stars had already lived and died in a span of cosmic history once thought far too short for that. The observations are solid. The puzzle is real. Either star formation in the infant universe was far more efficient than anyone predicted, or something about the early behavior of matter and dark matter isn't fully captured by current models. Rather than being a failure, this kind of gap between prediction and observation is exactly how science moves forward. Models get built, tested against reality, and revised when reality disagrees. Point that same telescope at a patch of sky no larger than a grain of sand held at arm's length, a spot that looks like pure blackness to the naked eye, and it doesn't find emptiness. It finds thousands of galaxies stacked at every distance, some near, some so far that their light has been traveling since the universe's earliest infancy. There is no truly empty patch of sky. Every direction examined closely enough turns out to be full. And still, all of this, the observable universe, its 2 trillion galaxies, its trillion stars, the entire 93 billion light-year bubble, is very likely just a small local fragment of something far larger. The evidence for this comes from the overall geometry of space itself. Precise measurements of that ancient background glow suggest that space, on the largest scales, is flat, not flat like a sheet of paper, but flat in the geometric sense that parallel lines stay parallel. Everything we can see would then be an infinitesimally small patch of something without any boundary at all. Not a small patch, but a mathematically zero-sized fraction of an endless whole. Even researchers who hesitate to embrace true infinity preferring the possibility that the universe is finite but extremely large, have calculated lower bounds for how big it must be to match what we observe. Estimates suggesting the total universe is at minimum somewhere between 200 and many thousands of times larger than the portion we can see, with no upper limit in sight. A theory describing an extraordinarily rapid burst of expansion in the first fraction of a second after the universe began, a period during which space is thought to have stretched by an almost unimaginable factor in a sliver of time far shorter than anything otherwise measurable, would have carried that same multiplication across the entire universe, not just our local patch. If the universe was already vast before that moment, it became almost incomprehensibly vaster afterward. If it was already infinite, it simply remained infinite. If the universe truly is infinite, and if the same physical laws apply everywhere within it, which every observation so far suggests they do, then basic probability leads somewhere strange. Given infinite space and a finite number of ways matter can be arranged within any given volume, every possible arrangement must occur again and again, infinitely many times. Regions identical to our own observable universe, down to the smallest detail, would exist elsewhere, over and over, forever. That's not mysticism. It's the straightforward consequence of combining infinite space with a finite set of physical possibilities. It's also completely untestable. Those regions lie. Whatever the true scale of the universe turns out to be, vast but finite or genuinely endless, the honest answer is that we cannot measure it directly, and quite possibly never will. We can map the observable slice with extraordinary precision. We can catalog its galaxies, trace its filaments, measure its expansion down to fine detail. But the whole of it, the true totality, sits beyond any horizon light can cross, forever a matter of inference rather than direct observation. Which brings the story back to something much smaller and much closer, the instrument doing all this measuring in the first place. A brain that evolved on open grassland, tuned to judge the distance to a water source, the speed of an approaching predator, the trajectory of a thrown stone, never once evolved to hold a number like 93 billion light-years, or 2 trillion galaxies, or a trillion stars. Our intuitive sense of scale tops out somewhere around a few dozen kilometers and a few decades of remembered time. Everything past that becomes abstraction, symbols on a page, numbers we can calculate with but never truly feel. That's why every attempt to describe cosmic scale eventually resorts to shrinking the picture down, imagining the sun as a piece of fruit, the nearest star as another piece of fruit sitting an impossible distance away, the whole observable universe compressed into something the size of a familiar object, just to give the mind something to grip. These comparisons help, but they're still, in the end, a kind of gentle deception, because even the miniature versions are too large to actually hold in the imagination all at once. There's a now famous photograph, taken decades ago by a spacecraft looking backward from the far edge of our solar system, showing Earth as a single, barely visible speck of light caught in a stray beam of scattered sunshine. From that distance, our entire planet is almost too small to register at all. Every person who has ever lived, every war fought, every idea conceived, every love and loss in the whole of recorded history, played out entirely on that speck, and that speck sits inside a solar system that is itself a rounding error, within a galaxy, which is a rounding error within a... None of this makes a human life meaningless. If anything, it does the opposite. Somewhere on that speck of dust, a species assembled entirely from the leftover ash of long-dead stars, managed, using nothing but patient observation and careful mathematics, to work out how large the universe actually is, to measure something 93 billion light-years wide, from a vantage point smaller than a pinprick, and to keep pushing the boundary of what's known a little further with every new telescope and every new generation of curious minds. The cosmos doesn't know we're here, doesn't care that we exist, and will keep expanding at the exact same pace whether or not anyone is left to watch it happen. It was never built with us in mind. And that, in the end, might be the most useful thing to take away from all of this. Your problems, your worries, the things that feel enormous and urgent in the middle of an ordinary day are real to you, but they are entirely local, tied to one small world, orbiting one ordinary star, tucked into one unremarkable arm of one galaxy among 2 trillion. The scale of everything beyond that doesn't diminish what happens here. It simply puts it in its proper place. Small, temporary, and, because of exactly those qualities, worth paying attention to while you can. You are standing on a fragment of stardust, looking up at a sky that stretches farther than language can really describe, and for a brief moment, in a universe that never asked to be understood, you understood a little more of it anyway. That's not nothing. Given everything you now know about the scale of what's out there, that might be the most improbable thing in this entire story.